So now we will be speaking about the application of ceramics material, okay, and the processing also. So the question will be, some question that will be addressed in this lecture is, how do we classify ceramics? What are some applications of ceramics? Of course, we have mentioned slightly in the previous session about the application of some of the common and well-known ceramics that we know. How is processing different than for metals? In metals, we have discussed about diffusion, cold work, annealing, etc. What about ceramics then? How will it different than for metals? So this is the taxonomy for ceramics. There is a glass type of ceramics. Yeah, this is usually used for containers for household, which we have in our home, and also optical, as lens, as the window, or as composite reinforced, in fiberglass structure, fiberglass composite. Usually, it has this glass ceramics also to reinforce the composite. Later, we will study composite in different chapter. Then clay products. Clay products, among others, this is also quite common in our daily life. We have whiteware, bricks as in our toilet, in our bathroom. Usually we have many of these clay products. Refractories, these are bricks for high temperature, usually used for furnaces. Then abrasives, used for sandpaper, cutting, polishing. And cements, although this can be considered as composite material as well, and it is used as structural material. Then advanced ceramics. This is more for engineering, for advanced engineering purposes. Usually biomedical applications, many biomedical applications use this advanced ceramics. So some ceramics used for engine, either as rotors, valves, bearing, also for sensors, in which we will discuss more in the sensor subjects. So the melting temperature for glass is moderate usually, that is why glass is usually easy to form in several hundreds of degrees Celsius, but large for other ceramics. And ceramic has small toughness and small ductility, okay, because it is not that easily formed. Large moduli and creep resist. It's very strong. It's not that easy to bend, not that easy to deform. Application of ceramics for high temperature, for wear resistant device, where wear resistance is required. Novel uses from the charge neutrality. Some glasses, in terms of application, some glasses can be easily formed, while other ceramics cannot be formed or cast. For example, let's see the application of refractories for furnaces. This will need a material that the material to use in high temperature furnaces. For example, we can consider silica or alumina system. This is a phase diagram. Unfortunately, due to time, we cannot. There is actually supposed to be a specific chapter on phase diagram if you look in the textbook, but we cannot cover it because of the time limitation. So, for example, here, if we would like to have very high temperature furnace, we can use this mullite, alumina and mullite or cristobalite composition, because this as candidate refractories, because they can endure temperature as high as 1,600 degrees Celsius. So a phase diagram shows the phase of the material, the structure of the material as a function of temperature and as a function of the composition. So in this case, for example, this is a composition of between alumina and silica. So when it is 0 like this, the alumina is 0%, silica is 100%. When it is 100 like this, silica is 0%, alumina is 100%. So mullite means this one, 67, about 67%. So it has 60, let's say 3 to 2, yeah. So 60% of alumina and 67% of alumina and 23% of silica, something like that. Another application of ceramics is as die blank. Remember in the cold work, yeah, for metal, where the material is being pulled like this using tensile force in order to have smaller cross-sectional area, so that then the dislocation becomes more entangled and then becomes stronger material. The die itself usually is made from ceramics. Yeah. Why? Because it needs wear-resistant properties. Yeah, because it is always in friction with the metal that is being pulled in between the two dies. Like this. So the die surface is made from is coated with 4 micrometer polycrystalline diamond particles that are sintered onto a cemented tungsten carbide substrate. This is, for example, the particle of the diamond particles of diamond sintered onto the tungsten carbide substrate. So the polycrystalline diamond will help control the fracture and give uniform hardness in all directions. Then application of as a cutting tool. Yeah, I have mentioned this multiple times during the course. Yeah, not only at this day of ceramics, but previous day also that mentioned that ceramics usually because of their hardness, they are used as cutting material, cutting tools. For grinding glass, tungsten carbide, and ceramics, for cutting silicon wafer, for oil drilling also, or if you remember like project that makes tunnel, like MRT, they use large drilling machine. Usually at the front of the drill bit, it is coated with ceramic material. Yeah, either diamond, polycrystalline diamond, or maybe silicon nitride or silicon carbide. So to make the drill bit stronger, so this can use single crystal or polycrystalline diamond in metal or resin matrix, something like this. This is the coated single crystalline diamond, and yeah, they are in resin. The resin becomes the matrix. The diamond is inside that matrix. Polycrystalline diamond resharpened by microfracturing along the crystalline planes. Then application as sensors, which we will discuss in further detail during the sensor and measurement course. So for example, like oxygen sensor, zirconia. Yeah, the sensor here usually they are used as chemical sensor, as a gas sensor. Why is that? Because as we know that, as we have learned in the previous session, that ceramics has defects, either Schottky defect or Frankel defect. Yeah, with this, the defects can be filled in by gas, yeah, from the atmosphere, and then it will cause charge neutrality to shift, and as a result, then electrons can travel, so they can be either a conductivity change or resistance change. So in the oxygen sensor that uses zirconia, the principle is to make diffusion of ion fast for rapid response. Yeah, for example, you have calcium impurity that will remove a zirconia plus and an oxygen 2 minus ion. So 4 plus and then plus 2 minus equals to 2 plus, this one. So when introducing like this, introducing this calcium 2 plus, then we will make a vacancy of zirconium and oxygen. So this vacancy can be filled in by oxygen from the surrounding atmosphere. Okay, and then it will cause another shift of the charge neutrality. So adding calcium impurity to zirconia will increase oxygen vacancies and increases the oxygen's 2- diffusion rate. Because of this vacancy, oxygen can move from the other side to this place. So the vacancy also move, the oxygen also move. So which is ruled by the diffusion law, which we have learned also in several weeks ago. Voltage difference produced when oxygen 2- ion diffuse from external surface of the sensor to the reference gas. Here, we have here gas with an unknown higher oxygen content, reference gas at fixed oxygen content. Due to the diffusion, the oxygen, and because also there is a vacancy inside the zirconia material, oxygen can diffuse from this place to the other place. Yeah. Then, due to this diffusion, since this brings ions, 2- ions, means there is a current flowing, right? Voltage difference is produced. How to fabricate ceramics then? This first is by glass forming. Yeah, for example, we have a mold here, and we have a GOP, yeah, ceramics at high temperature, like this, and put into the mold by pressing. This will form the glass shape. Then it is the suspended parison here, and then put into a finishing mold. And after that, a compressed air is being blown inside this cavity and to form the structure, the glass structure. Or then fiber drawing. Fiber drawing is, for example, if we want to make fiberglass, optical fiber from glass fiber, like this. This is molten glass, and then it is being pulled, yeah, at this very thin, as a thin fiber, and then went up. It plates dishes or chip glasses. To form sheet glass also by sheet forming using process called continuous draw. Originally, the sheet glass was made by floating glass on the pool of mercury. So this is glass sheet. Okay, so this is the molten glass flowing here. There is a water cooling here, and this becomes solid. It solidifies here, and then forming by this forming roll becomes a sheet. It is turning roll. It is moved through here, and then eventually it becomes glass sheet. So the glass structure itself is amorphous. Yeah? That is why it has low strength, low flexural strength, and also low Young's modulus. So this is the basic unit of silica, silicon tetraoxide, yes, silicon oxide with 4- tetrahedron. If it is quartz, silicon dioxide, then it is crystalline, like this. But it is glass, it is amorphous, and the amorphous structure can occur because we add impurities like sodium plus, magnesium 2 plus, calcium 2 plus, or aluminum 3 plus, so that it cannot make crystalline structure. Because the impurity interfere with the formation of the crystalline structure like this. It becomes soda glass. This is the glass that we use for glasses that we use daily. If you put boron borosilicate glass, which becomes stronger Pyrex glass. Another fabrication method is called as particulate forming. This is by first milling and screening the desired particle size, mixing particles in water to produce a slip, and forming a green component, yeah, like this. Hydroplastic forming, extrude the slip into a pipe. Like this. The slip is extruded by pushing here, then pushing the bill, and then it forms an extrusion. Or by slip casting here, pour the slip into mold, absorb the water into mold. This becomes a ceramics. Or if you want to make a hollow component like this and then turn upside down, so that this one will go out, and then we form a hollow component, yeah, with a cavity in the middle. Like this. And after that, we dry and fire the component to strengthen the structure. Clay is one of the widely available ceramics on Earth. The mixture component are clay 50%. It is a filler, usually from quartz, finely ground, and fluxing agent like feldspar, which binds the components together. The feldspar itself consists of aluminosilicates, which means aluminum and silicon and oxide, and with additional impurities of potassium, sodium plus, and calcium plus. Clay is very cheap, inexpensive. When we add water to clay, the material could shear easily. That's why when we put water, it can be formed more easily compared to if it is dry. And the shearing occurs easily along the weak van der Waals bond, like this. When we put shear along this weak van der Waals bonding, it can deform easily. This will enable extrusion and also enables slip casting. This is structure of kaolinite clay. Some structure of clay is quite complex also, like zeolite. You remember, if you ever heard about the name zeolite, it is also one can be used as engineering material, as filter, as membrane also. And the material is quite abundant at least in Indonesia, and can be used for various filtering or membrane application by adjusting the porosity structure. Then after forming, usually forming in slip casting or extrusion, then the next step is drying and firing. By drying, then the layer space, the layer size, and the spacing between the structure will decrease. Okay, so this is, for example, in the wet slip, in the ceramics. When it is still wet, it is easily, we can form it easily. When it is partial dry, it is like this. When it is green ceramic, when it is completely dry, then it has fixed structure, and it's difficult to shear again. Drying too fast will causes the sample to warp or crack due to non-uniform stickage. During firing, the temperature is raised to very high temperature. This is used in when you make ceramics, when you make houseware, bricks also, ceramics in your toilet. Then the final step is firing. Very high temperature, 900 to 1400 degrees Celsius. A process of vitrification will occur. In this case, liquid glass will form from clay and flow between the silica particle, silicon dioxide particle. The flux melts at lower temperature. For example, this is the silica particle, the quartz. The glass formed around the particle. This is a micrograph of porcelain. Then another process for particulate forming is called sintering. This is useful for both clay and non-clay composition to produce ceramics and glass particles by grinding. Then to place the particles in mold, then press it at elevated temperature to reduce the pore size. So for example, this is aluminum oxide powder. After being sintered at 1700 degrees Celsius for 6 minutes, so the pore size is reduced. Then there's a process called powder pressing. In sintering, the powder touches to form necks, and gradually the necks thicken. So between the grain, they form necks and then thickens. Add processing aids to help form necks, and it will have little or no plastic deformation. If the powder pressing can be done in uniaxial compression, where it is being compacted in single direction using hydraulic compression, for example, or isostatic hydrostatic compression, applied by fluid in a rubber envelope, or hot pressing by using pressure and heat. Okay, so initially it was like this. So after powder pressing, it will form grain boundary like this, neck in the grain boundary, the boundary between the grains. Then further pressing will cause the pore structure to be smaller, and the neck will thicken. Then a process called as tape casting, where thin sheets of green ceramics is casted as flexible tape. And this is the source of the slips of the molten one, and then flows through the doctor blade here and becomes very thin layer of the ceramics. After that, it taken up by this reel. This is used for integrated circuits and capacitors, cast from liquid slip ceramic plus organic solvent. Finally, the third part, the type of ceramic fabrication method is called cementation. Produced in extremely large quantities, for example, in the type of Portland cement, the clay is mixed with lime-bearing materials and then being calcinated or heated at 14 degrees Celsius, 1400 degrees Celsius. And Portland cement here consists of tricalcium silicate and decalcium silicate. When water is added, it will produce a paste which will harden. And hardening occurs due to hydration, chemical reaction with the water. After that, it is being formed, which is done in minutes after the hydration begins. So advanced ceramics are used, as mentioned also in the previous slide, for heat engines, for example, as the blade, as a rotor, component, etc. The advantages of using ceramics is they can run at higher temperature. For blades or turbine that needs to be at high temperature, then you have to use ceramics. It has excellent wear and corrosion resistance, because corrosion, it doesn't react with, doesn't electrochemically react, it's quite inert because it is always in charge neutrality. Wear, because excellent wear properties, because it doesn't scratch, because it is very hard. No slippage, no slip plane, low frictional frost losses, and the ability to operate without a cooling system, because it can endure very high temperature. While in metal, it may melt, or if not melt, then it may there is an expansion of the metal, due to thermal temperature. And low density. The disadvantage of ceramics, on the other hand, is because it is brittle. It breaks easily when the force is above certain threshold. As I gave example with glass window, for example, compared to metal. Too easy to have voids, which will weaken the engine. And finally, the final difficulty is too difficult to machine. Machining is required to make certain form or shape of that material. With metal, it is easy to machine. You can use electrical discharge machining, EDM. Even now with metal, you can use 3D printing. Ceramics is not that easy. Ceramics is not that easy. Usually, the process until now, you have to use mold, casting, like that. Possible parts that are made from advanced ceramics, like engine block, piston coating, jet engines, using materials like silicon nitride, silicon carbide, or zirconia. Then application of advanced ceramic. This is a ceramic armor. Remember, if you watch movies, police cops usually have this armor made from thin material of ceramics, made from aluminum, boron carbide, silicon carbide, or titanium boride. It's very hard material. It will shatter the incoming projectile. The energy absorbent material is located underneath, usually coated with also another polymer to absorb the energy. So that then the shock doesn't give too much shocks to the wearer. Another application for advanced ceramic is for electronic packaging to securely hold microelectronics and provide heat transfer. Yeah, it must match the thermal expansion coefficient of the chip and the electronic between the chip and the electronic packaging material. Other requirements include it has to have good heat transfer coefficient, so the heat can be transferred easily outside, but poor electrical conductivity, must not conduct electricity. An example of such material include like boron nitride, EN, silicon carbide, and aluminum nitride. Aluminum nitride has good thermal conductivity, even better than alumina, 10 times much better than alumina. Good expansion that will match with silicon. And as you know, that in microelectronics, usually they use silicon-based material. So as a summary of this application processing, ceramics can be categorized into these basic categories: glasses, clay products, refractories, cements, and advanced ceramics. The fabrication techniques, there are three main techniques: glass forming, where impurities will affect the forming temperature; particulate forming from particles size, needed if ductility is limited; and cementation when we need large volume and at room temperature process. Heat treatment is used to alleviate residual stress from cooling and to produce fracture-resistant component by putting the surface into compression. Okay, so let's have groups again.